Hey everybody, so welcome back to our next derivatives video. In the last one we kind of covered what a derivative is and the quick way to calculate it. So you guys will most likely end up going over the formal limit or the formal definition of a derivative, which takes a lot longer than the actual shortcut that we used, which is the product rule. So in this video, we're going to do 2 or 3 examples. We're going to do all 3 of these examples actually, kind of showing you how the product rule works, and we'll go through it both algebraically and graphically. And then we'll start tackling some applications of derivatives, the tangent line problem being the most common application. So first off, let's start off with our 3 questions here. The first one says f of x is equal to 5, so what is f prime of x? Now, it's basically asking what is the derivative of 5. So algebraically, we can think of this function as 5 times x to the 0th power, because anything to the 0th power is just 1, right? And 5 times 1 is 5. Well, looking at the formal definition of a limit, or looking at the product rule we used actually, it's not the formal definition. Whoops, let me go ahead and just erase this. But if you remember, or if you recall the product rule shortcut that we used last time, you'll notice why the answer to this problem makes sense. I'll just go ahead and write down the answer, which is 0, and we'll go through why it works. So x to the 0, if we already used the product rule on this term right here, what would we get? Well, notice that the product rule is n times x to the n minus 1 power. If we were to use that with x to the 0, we get 0 times x to the negative 1, or just 0 times the 1 over x, which is always going to be 0. So therefore, we end up with 5 times 0, which is just equal to 0. And now looking at it from a slightly more graphical point of view, let me see if I can squeeze in a graph right here. Actually, let's go with a smaller graph, just so we have space. So the line f of x equals 5, or just y equals 5, is just going to be some straight line right here, right? So if you were to take the slope at any point on a straight line, that slope is just going to be 0, right? It's just a straight line. If you take the slope of a straight line, it's just a line, which in this case is going to be 0. So this leads me to tell you something important that you should note down, which is if you have a function that is a constant, so any number or decimal, if you have a function that is just a constant, so no variables, the derivative of that function will always be 0. So that's one important thing to note down. Moving on to the next problem, we're going to go ahead and I'll write down the answer over here, and we'll go ahead and walk through this algebraically. So using the same power rule thing, we have 2 times, and then using the power rule on x squared, we get 2 times x to the 2 minus 1. So we can multiply these parts together to get 4, and x to the first, or just 4x. Now algebraically, we get 4x. What about graphically? Well, if we were to graph this, our x squared is going to look like a parabola, and then adding the 2 on should be slightly stretched out maybe. So just a quick rough sketch. Okay, so what if we were to take the derivative of this function at any point? Well, even though we know our answer is already 4x, if you kind of take the derivative at any point here, you know that you're going to get a line. So first off, we know that it's not a constant because it's not a straight line, but it has a slope, meaning that it has a slope that is greater than 0. And because of this, the slopes are also different. If you look at the line over here and the line over here, you'll notice that one has a slope that seems to be positive and the other has a slope that seems to be negative. So you know that the derivative of a function with the term x squared cannot be just a 0 or just a number, which is why you have your accompanying x when you look at it even graphically. So even graphically, this makes sense. Now moving on to the last one, we'll just go through this algebraically because you should have gotten a sense of how this works graphically as well. Okay, so you'll notice that this has 3 terms, which means we're going to have to take the derivative of each term separately. So why does this work? Well, the derivative, right? So if d over dx, or the derivative of term a, plus the derivative of term b is going to be equivalent to the derivative of term a plus b. So this is something that you're going to use in multi-term functions like this, such as quadratics, most often. But this is key to note because this allows us to take the derivative of the individual components of the function, and that becomes the derivative function. So what does this mean? Well, we can just take the derivative of each individual component and we'll get our answer. So taking the derivative of 6x squared, we get 6 times, using the power rule once again, 2 times x to the 2 minus 1. So this gets us 12x. Now plus 2 times, well, this is x to the 1, so 1 times x to the 1 minus 1. Well, x to the 0 is just 1, so this gets us plus 2. And then plus 3 times 0 times x to the 0 minus 1. And that's just 0, so we can go ahead and just, that becomes plus 0. So our final answer becomes 12x plus 2. So that is the derivative of our function. Great, so hopefully you guys got a basic sense of how to do derivatives from these types of problems. We'll cover trig derivatives sooner on, since those are slightly more complex. But let's go and do one quick example of one of the most common applications of derivatives, and that is the tangent line problem. So if you remember from the last video, a derivative represents a slope. And if you take your line, your equation that you have for a line, the m value right here also represents a slope. So there will be many problems where you end up finding an equation in the form of y minus y1 is equal to m times x minus x1. So whenever you do this type of problem, that m value right there, that's the derivative. So maybe they want you to, you're given a function f of x is equal to 2x squared plus 3. And let's say, what is the equation of the tangent line? So I'll just write it tan line at x equals 5. So this may be a AP problem that you get, or just a test problem, but this should really take about 1, maybe 2 minutes. And let's go ahead and talk about why. So we're going to be given the point 0, 3. Okay, so what do we know in this question? It's asking for the tangent line, right? What is the equation of the tangent line at x equals 5? So the first thing you do when you see a problem like this, right, is you want to take the derivative of a function. So you want to find out what f of x is, and using the power rule we get 2 times x to the 2 minus 1, and we know that the derivative of any constant is 0, so we can just cancel that out. And what does this get us? Well, this just gets us 4x. So that's the derivative. But it says what is the equation of the tan line at this specific value, so we have to find out the derivative at that specific value. And that's just 4 times 5, which is 20. So now we know the derivative at x equals 5. In other words, we know what the slope of our function is at 5. Now you can check this out by graphing it, of course, but that's what the derivative means. So what is the equation of the tangent line? Well, that's basically asking for this format when it asks for the equation of a tangent line. And now you have all the components you need. So your equation is going to become y minus, well, what's your y1? That's 3, is equal to m, which is your slope, or the derivative, 20 times x minus x1 is 0. Now you can leave it like this on an AP test, but if maybe you've used the y equals mx plus b form instead, so you're used to that, you can also take the time and convert it into y equals mx plus b. In other words, this just becomes y equals 20x plus 3. And that becomes the equation of the tangent line at this specific point. So that is one of the most common applications of derivatives you'll see.